event. Professor Hans MUNTHE-KAAS. He is a professor in mathematics at the University of Bergen, Norway. And he is also currently a chair of International Abel Prize Committee. As we know, that the Abel Prize is one of the prestigious prizes awarded by the King of Norway to one or more outstanding mathematician in the world. Our warm welcome also to all colleagues and students for attending this program. Thank you so much for your enthusiasm, and we are really appreciate it. Hello, Hans. How are you today? Good.
It's a bit early for me. It's just 8 o'clock in the morning, so I just got out of bed. But it's fine, yes.
It's great to see you, even though virtually. How's life in Bergen now? Are you free now from
It is we are ending the term now, so I've just finished my lecturing for the fall, and we're going into the exam period. And in this time of the year, it's dark here. I mean, the sun rises at 9:30 and sets at 3 o'clock, so it's short days and quite rainy. So it's not the most inviting period to stay in Bergen, but we're looking forward to New Year, and then probably we get snow and so on.
Yeah. I hope everything is fine, getting better and better there. Yeah. And now I'm very happy that you received my invitation to give a lecture in this series. I remember your last visit to ITB. That was in 2018, right?
That's right. Yes, 3 years ago. Yes.
And I remember that you enjoy playing angklung.
Okay. I still haven't found anyone.
Yeah. Angklung. Okay. And hope next time you can visit us again, and even more we could strengthen our collaboration.
Yes.
And as I
okay, I'm coming when you invite me.
Okay, good. Okay, and now the audience today is not only from Indonesia, as you know, Hans, but also from neighboring countries, from Malaysia, Philippines, Thailand, and then some of them from India. In the registration, it's about 100 people registered in this event. So hopefully we'll come more and more, in this time. Okay, so ladies and gentlemen, this Mathematics Distinguished Lecture Series is organized by the Department of Mathematics, Faculty of Mathematics and Natural Sciences, Institute Technology, Bandung. And in this series, we have opportunity to meet and discuss with famous mathematicians from various countries to explore the role of mathematics from various fields. And with this lecture series, we hope that we could foster and also promote the culture of doing mathematics, as well as highlight the prominent role of mathematics in shaping future society. And now, this afternoon, we are all very excited and honored to have Professor Hans MUNTHE-KAAS from the University of Bergen, Norway. And his talk will be chaired by Dr. Novriana Sumarti. But before I hand it over to Dr. Novriana, I would like to invite the head of the Institute for Research and Community Services, ITB, Dr. Yuli, to give a welcoming speech. Dr. Yuli, the time is yours.
Thank you, Professor Edi. Similar with Professor Edi, good afternoon and also good morning and good evening to all of you accessing this lecture series from various time zones. Greetings from Institute Technology Bandung. My name is Yuli Setioindartono. I currently the chair of ITB, Institute for Research and Community Empowerment. It is a pleasure and joy for me on behalf of ITB to deliver some remarks on the third event of ITB Mathematics Distinguished Lecture Series. I'm truly delighted to preview the list of guests registered for this occasion, which listed a wide spectrum of audience brought together for the cause, the ITB Math Distinguished Lecture Series. With all my humble appreciation, I would like to welcome you all to ITB. Let me express my appreciation to the initiator and organizer of the series, and especially to Professor Edi Tribaskoro for all the concerted effort to bring this series of lectures to ITB. This initiation is truly consistent to the spirit of ITB to become a beacon of knowledge nationally, regionally, and beyond. My profound appreciation and gratitude goes to our prominent guest, Professor Hans MUNTHE-KAAS, a professor of mathematics at the University of Bergen, Norway. I check in the internet, Professor Hans right now at Oslo, the temperature is 2 degrees Celsius, right? That's very good.
Sorry?
I think.
What did you say? How much?
2 degrees Celsius?
Could be.
Yeah, in Oslo, Norway right now. So thank you.
It's a bit warmer. We are on the west coast, so it's a bit warmer on the west coast. So I would think around 10, but I don't know.
Okay. A part of being a world expert in computational mathematics, Professor MUNTHE-KAAS presides over the prestigious committee of International Abel Prize. Professor MUNTHE-KAAS, on the behalf of the Institute Teknologi Bandung, I thank you for all of your effort to share your extensive experience with us. You are among exceptional mathematicians, equally at ease doing pure math and simultaneously directs various prestigious organizations and committees at a very high level. We are eager to learn from your experiences in looking the panorama of mathematics from the very high point of view. I have learned that this is not your first time visit ITB. In fact, you have been here to ITB a few years ago in person, not only by virtue of the internet. We are hopeful that our relationship will only flourish. With this series of lectures, we hope to highlight the best of and the many faces of mathematics, from the very people who are carrying the torch of mathematics, intriguing mathematics, inspiring mathematics, applicable mathematics as well. Along the way, we are hopeful that the spirit will infect many souls touched by the Queen of Science. Thank you again, and I hope that you will enjoy Professor MUNTHE-KAAS' lecture. Thank you, Professor Edi, for this time.
Okay, thank you very much.
Thank you,
Yuli, for welcoming speech. And now, before I let to, okay. And now, before I let to Dr. Novriana to share this session, let us have a group photo first. This is a very important photo. Okay, Pak Rudy, can you help us?
Yes, everyone, please turn on your camera. We have 3 pages here. So yeah, you can comb your hair first.
Okay, good.
Okay, for the first page, I'll take the picture. 1, 2, 3. And then the second page. 1, 2, 3. And then the last one, 1, 2, 3. Okay, that's all. Thank you very much, Pak Edi.
Okay, so thanks, Pak Rudy. And now I let Dr. Novriana to chair this session. Please, time is yours.
Thank you, Professor Edi. Let me introduce myself, Professor MUNTHE-KAAS. My name is Novriana Sumarti. I work at ITB as well. Yeah. And then I'm coming from industrial and financial mathematics. And before we continue to listen to the presentation of our distinguished guest here, let me read your brief curriculum vitae. So I want to share first. Okay. Can you see my presentation? No?
Not yet.
Not yet.
Yeah.
Okay.
Okay, good.
So let me read a brief curriculum vitae. Sorry, should be in presentation mode. Okay. Professor Dr. Hans MUNTHE-KAAS, he works at Department of Mathematics, University of Bergen, in Norway. He got MSc in 1986 and PhD degree in 1989 from Department of Mathematical Sciences, Norwegian University of Science and Technology, or NTNU. Honors and awards that he received, including Carl-Erik Froberg Prize in Numerical Analysis in 1995, Exxon Mobile Research Award for Best PhD, NTNU in 1990, and Jubilee Scholar, NTNU Trondheim, Norway, in 1986 to 1989. And then he got elected membership of academics from the Norwegian Academy of Science and Letters, the Royal Norwegian Society of Sciences and Letters, and the Norwegian Academy of Technological Sciences. As Professor Edi said before, he is participating in Commission of Trust recently as a chair of the International Abel Prize Committee from 2018 to 2020, and as a member of board on the Abel Prize in Mathematics from 2010 to 2018, and as a president of the Scientific Council of SIMPA from 2017 to present.
Well, it finished last year. This presidency
it's already
there.
finished.
So, yes.
Okay, sorry. And
Yes.
then as a editor-in-chief and editor board of Journal Foundation of Computational Mathematics from 2012 to present. Is it okay? It's already yes, still in editor as
Yes.
editor-in-chief. And you serve as a secretary and member board of director for the Society for the Foundation of Computational Mathematics from 2005 to present. And I found at least 6 academic articles in on the University of Bergen website. First is the recent one is planarly branched rough path and rough differential equation on homogeneous spaces, published in Journal of Differential Equations, and invariant connection Lie algebra actions and Foundation of Numerical Integration on Manifolds, published in Science Journal on Applied Algebra and Geometry in 2020. And then the other academic articles published in lecture notes in Computational Science and Engineering, Abel Symposia, Springer Proceedings in Mathematics and Statistics, Journal of Geometry and Physics, and Foundation of Computational Mathematics, and also in lecture notes in mathematics. So I just wrote the recent 5 years of Professor MUNTHE-KAAS publication. And that's all the brief curriculum vitae of Professor MUNTHE-KAAS. We are going to listen to the presentation with title Concrete versus Abstract in Computational and Beyond Mathematics. For all audience, I invite you to write your questions in the chat of the Zoom platforms. Thank you. So, Professor MUNTHE-KAAS, time and screens are yours.
Thank you, Novriana. So I'll share my screen. Yeah, you see it there?
Yes.
Yes, we
Okay.
already.
Yes. So I do it differently than when we tried out before, but I think it should be better for me because now I can see the screen at the same time. Okay, so my talk is a bit of a talk about mathematics without really doing a lot of mathematics in the talk, but I have a view of certain developments in the mathematics and that I think are important, and I want to convey this this view. So the title is Concrete versus Abstract in Computational and Pure Mathematics. So I did start with putting up a bit of questions that were somewhat motivating for the discussion I will go into. So the first question is, in the 20th century, there was a development sciences, the gap between pure mathematics, and the gap during the 20th century became so deep that people from the two communities could hardly speak to each other because they were using different tools, different machinery. They were discussing perhaps sometimes the same things, but in very different languages. So what caused this gap? Next question, what is the difference between concrete and abstract formulations of mathematics? What does it mean that something is abstract, and what does it mean that it's concrete? Are abstractions good or bad? I mean, it seems to be making things more difficult to abstract things, but perhaps not. That is a question. Another important question, which is a bit of a mystery perhaps to people outside mathematics, is we have centuries of accumulated knowledge in the mathematical sciences, and still it is so that a fresh student starting in university to study mathematics can, within the study of, let's say, 3 to 4 years, learn very much of the mathematics of the previous centuries. And how is this possible when the amount of knowledge is just accumulating all the time? How could it be that it's possible for a fresh student to get on top of this in a reasonably short time? One should think that every century it would become more and more difficult to get into the mathematics, but it doesn't seem to be like that. The two central questions of this talk is, can computational mathematics benefit from abstractions of pure mathematics? And the other direction, can pure mathematics benefit from computational ideas? And the last two questions are, is it so that mathematics is always becoming more and more specialized, and is so that we are just looking at smaller and smaller pieces of mathematics, or is there some kind of unifying trends in mathematics in our time? that's sort of the basic things that we will discuss in this talk. And the answers that I will try to convey to you is that the central issue in the discussion of all these questions is the relations between the concrete and abstract versions of mathematics. So that's the central topic of this talk. So let's start to think about what does it mean that something is abstract, and what does it mean that it's concrete. And if you look at abstraction in Wikipedia, that's general. It's not only about mathematics, but abstractions in general. They write that abstraction is a conceptual process where the general rules and concepts are derived from the usage and classification of specific, real or concrete examples, first principles, or other methods. So I hear a voice.
Jadi nomor satu. Ya, tepatnya mungkin kayak aku nggak kalahin gitu sih.
There is a voice coming over.
Sorry, it's just noise.
Okay.
Sorry, please continue.
Yeah. So as abstraction, abstraction is abstraction is the process where you start from examples and concrete realizations, and you try to abstract some common features of these examples. So in mathematics, I would say that abstractions discard
Professor MUNTHE-KAAS, sorry, Professor, I cannot hear your voice. Professor Eddie, can you hear Professor MUNTHE-KAAS' voice?
No.
Oh, so there is some trouble.
In fact, we lost the sound for maybe half a minute.
Yeah. It's, now I can hear you, Professor MUNTHE-KAAS.
Hello.
Oh no.
Muted.
Yeah, I think Professor Kaas also cannot hear our voice, maybe.
Yeah.
Is it possible to text to him?
Let me. Hans, Professor Hans, we couldn't hear your voice.
And a concrete version of matrices is that is a collection of numbers where we use this array of matrices to define basic operations such as matrix products and matrix vector products and inverses and so on. This is a concrete version of linear algebra. The concrete version has different realizations. If you want to program this, it's various ways you could do it. For instance, for matrices and vectors, representations. If you have a matrix with many zeros, you don't need to store all the zeros. You don't need to treat all the zeros when you do the computation. And or you could store them as dense matrices. So there are various ways of representing this same structure. But I mean, in the computer, a class for dealing with a program for dealing with sparse matrices would look very different from one working on this. But essentially, it is all describing the same mathematical underlying phenomenon. So the various discrete realizations. And on the other hand, you have the abstract definition where you say that, okay, a vector space is you have a set, and you have a vector addition, and you have scalar multiplication, such that they fulfill the normal laws of these things like A plus B plus C equals A plus B plus C, etc., etc. And you define linear operators between spaces. Instead of talking about matrices, you would talk about a linear operator taking one type of vectors to another type of vector. And then the matrix would, from the abstract definition, the matrix would be just a representation of the underlying concept of a linear operator between vector spaces. The tensor product in that case would be described in terms of a diagram, and this will be I'll be returning to this kind of ideas later. So the idea here is that if you have two vector spaces, you can form a vector space you would call the tensor product, which has the dimension of the first space times the dimension of the second space. And this, as a linear space, this object, the tensor product, could be characterized uniquely by a certain property. The property is that, first of all, you have this map taking you in here that we could call the tensor product. So you have a map taking pairs of vectors and producing combined vector. It would be like taking A and B and producing A times B. And this should have the property that if you pick any other vector space and you pick a bilinear mapping down to this vector space, then there should be a unique linear map here, so that this diagram commutes, so that this composed with this will be the same as going down here. This is a characterization of the tensor product by a universal property in algebra. So the interesting idea here, it's not really the details of what I'm saying, but the interesting idea is that you can characterize up to uniqueness, up to isomorphism. You can up to uniqueness in a mathematical sense. You can characterize such an object as the tensor product by talking about arrows into the object and arrows out of the object, and these arrows have in this case to be linear or bilinear maps. So this is an idea that this language of defining properties of objects can be expressed in terms of such diagrams, and the question is this can you essentially describe any kind of mathematics by this kind of diagrams? So let's go back to more philosophical views of this abstract versus concrete mathematics. Eugenia Chang, in her book The Art of Logic, simplification through abstraction. So the role of abstraction is to simplify things. It's okay. It looks like it's in abstraction. It might look more difficult, but the idea is really to simplify things. And she says the powerful aspect of abstraction is that many different structures become the same when you forget some details. And and therefore you can, if you have the right abstractions, you can discuss many different topics in the same setting. You could say that these are just different instances of the same underlying mathematical concept. This is an important thing, and this is also quite. It's important for the structure of mathematics, for the proofs in mathematics, and it's important for learning in mathematics.
the fact that abstraction is sorting out, throwing away a lot of non-essential information is one of the reasons. That's the essential answer to the question of how a young student can learn so much of the older mathematics, because you understand much more of the abstractions behind it. Sir Michael Atiyah, on this last issue of students and research building upon previous experiences, wrote like this: the aim of theory really is, to a great extent, but this was for all sciences really, but I think that it's even more true for mathematics. The aim of theory really is, to a great extent, that of systematically organizing past experiences in such a way that the next generation, our students and their students and so on, will be able to absorb the essential aspects in as painless a way as possible. And this is the only way in which you can go on cumulatively building up any kind of scientific activity without eventually coming to a dead end. What does it mean by coming to dead end? I think what is aiming at is if you were just doing the same way of doing mathematics over the centuries, the accumulated knowledge would be so vast that it would be impossible to understand everything. But when you introduce abstractions, you can throw away a lot of unnecessary details, and you can focus on the basic ideas and the basic structures, and that is the important point. And it's even more, I would say, it's even more important in mathematics than in other sciences, because the difference between mathematics and let's say physics is that in mathematics we establish truths, we prove theorems, and once it is proven, it is for all future, it is established as a truth. There is no question about it. And nobody can take it away. It is proven. So the old masters like Euclid and so on, they proved theorems that are, and algorithms that are as important today as they were 2000 years ago. So there's no way of throwing away mathematics, but you can throw away details by doing abstractions. In physics, it's different. You have one theory that is discarded because it's found that it's not exactly correct, and so you'll always have in other sciences the falsification of theories that they are eventually becoming obsolete, but not so in mathematics. So I want to look a little bit into the developments of pure mathematics in the 20th century. And the 20th century was really the century where pure mathematics where the main object of study is mathematics itself, was developed extensively. It was before the 20th century, I would say that the division between pure and applied mathematics was not so big. Mathematicians were doing both. But then in the 20th century, there were certain developments that focused on abstractions that led to far-reaching advancements in pure mathematics. So and all this is around the abstractions, and this is the development of the 20th century. So it started probably with work on symmetries in the 19th century. Mathematicians such as Abel and Lie and Galois and other mathematicians were, and then Cartan were working on ideas of describing symmetries by operations on an object. So you could talk about the symmetries of an object, like this maze here. You can talk about the fact that everything is generated from reflections and rotations of a certain area. So the concrete ideas of symmetries were developed in the 19th century. But towards the end of the 19th century, the idea of symmetries were abstracted, in the sense that they defined abstractly the concept of a group of symmetries, and they detached it from the object on which this group is acting by saying that you have an abstract notion of a group, and then you have the idea that a group could act on an object. So and then you could talk about the group as something that is independent on the operations, the symmetry operations of an object would in itself be a mathematical object that you could use in theory, and it would make it possible to talk about groups in a general setting, and you could talk about things like two different groups that looked differently because they were acting on different objects, essentially were the same group. You could classify things, and that was really important. So that was the first major abstraction, I would say, in towards the end of the 19th century. The next abstraction that turned out to be very important was the abstractions in the field of mathematics called global analysis. So this is about differential equations and geometry of the differential equations. The idea here is to try to define abstractly what does it mean that you have a domain of a differential equation, what you need to be able to speak sensibly about differential equations. In early studies, people would say that the differential equation is living on a vector space. You define a differential equation on the vector space, let's say Rn, R3, R2, R3, R4. But that a vector space is really having too much information about the domain of a differential equation, and it's confusing certain things. So the idea that differential equations should live on vector spaces is not. It's confusing some concepts that should really not be confused. And in the early part of the 20th century, the idea of a differential manifold appeared, and the manifold is the domain of general differential equations. The properties of a manifold are the following: that if you are in an area of the domain, you should be able to put in local coordinates by saying that, okay, locally any area can be mapped down to a Euclidean space. So you have a way of mapping things down to concrete vector spaces. And if you talk about mappings between two different manifolds, you would say that you study these mappings by looking at how they look in a certain coordinate systems on the first space and a certain coordinate system on the second space. So you give meaning to operations on the manifold by using local coordinate systems. But it turns out that the definitions are constructed in such a way that it's independent on which particular coordinate system you're using. You could use any coordinate system and you could get the same notion. So the ideas of differential manifolds is that they exist independently of particular coordinate systems. And therefore you can talk about properties of differential equations without having to express these differential equations in a given coordinate system. This is a powerful concept. So, and Sophus Lie, he worked in the Norwegian mathematician Sophus Lie, he worked with the symmetries of differential equations in the 19th century. He was looking at symmetries of concrete differential equations in a concrete setting. He did not know about manifolds. It was in the 20th century with Cartan and others that the ideas of Lie was abstracted to Lie groups, which are symmetries that are also differential manifolds, and this was a very powerful concept that is crucial to modern physics. So global analysis. The other idea of a differential manifold, it has the possibility of taking local coordinates, and it has the possibility of talking about tangents. So if you're in a point and you are, so that's a position of a particle, you could always talk about the velocity of a particle. So that's the essential structure, and that's called a tangent manifold, a set of all tangent directions on the manifold. So that was a geometric abstraction that was really important in many contexts. The third abstraction was all the abstractions that took place in abstract algebra. A revolution in the 20th century. A lot of algebraic structures were discovered and developed. I would say that at least in the first 2/3 of the 20th century, the focus of abstract algebra in this kind of text was mostly on existence, uniqueness, and classification of various algebraic structures. not so much about efficient computation and how you could really implement these things on a computer. You see here the picture on the front here is a certain diagram. Again, this is similar to the diagram we saw in the discussion of tensor products. It's a way of relating various algebraic structures by mappings between the structures. So that's the third great abstraction of mathematics in the 20th century. That is something called category theory. The category theory is a bird's eye view of mathematics. It's a high level view of mathematics. It's discussing mathematical objects by objects and morphisms. So to be very concrete, you could talk about the category of all linear spaces, where these objects would be linear spaces, and where the arrows would be linear mappings between the spaces. And an important thing of categories is then that you have always this composition law, so that if you take a composition of two linear mappings, you get a linear mapping. These kind of things. But it was made into a profound theory where you could really discuss lots of mathematical properties of objects, and you could do it without being very specific about what sort of structures you were discussing, because it turns out when you do it in this setting that a lot of properties can be developed in a rather general manner. So it would be a lot of the structures you could do it for, let's say, for vector spaces, or you could do it for topological spaces, and you would have the same type of categorical descriptions of operations. So the question is, how far can you get by probing the properties of a space by arrows in and out? And in this theory, there is something called the Yoneda lemma, which I'm not describing properly, but a consequence of this Yoneda lemma is that any object in the category is entirely determined by its relation to the other objects in the category, and as encoded by the transformations to or from the object. So that's Eugenia Cheng again says that category theory is the mathematics of mathematics. So it's a very powerful tool. It's essential to developments in topology, and also in computer science actually nowadays. I'm talking about now computational science. So computational science is of course how to do computing on various structures, and when I say computational science, I mean the computations that are also related to applications outside mathematics. When I talk about computational mathematics, I'm mostly thinking about computations that are solving problems within mathematics. But in computational science, I would say that the computational science is the third way. If you have the classical ones of theory and experiments, and computation is the third way. So like if you want to investigate the structural properties of some mechanical device, you could do it by theory, by experiment, or you can do it by, as here, a computation where you, for instance, compute the stresses by dividing it into small triangles, and compute the stresses by something called the finite element method. That's very much used in engineering sciences, of course. This idea of doing computation goes back to at least to Kepler. I would say that Kepler was interested in doing the understanding the observations of Tycho Brahe of the solar system. What is the structure of the solar system? What are the laws for the orbits of the solar system of the planets? It was so much observations from Tycho Brahe that he was really reluctant to take on the job of computing everything, because it was so much work. Then came the invention of Napier, where he invented the logarithm, the table of logarithms, and multiplication just became the sum when you look it up in the logarithm table of Napier, and that was a tool that he used to compute the laws of the solar system. Here's another example that you might have seen before. Norwegian mathematician Carl Sturmer and physicist Christian Birkeland, they were interested in explaining the aurora borealis, the polar lights, 100 years ago. Birkeland had a theory that this was all because of charged particle in the magnetic field. Carl Sturmer wanted to prove this, and he wanted to see how the particles move in the magnetic field. And he developed something called a symplectic integrator, which is it's kind of a method for integrating mechanical developments. And he needed a computer, so he he trained his students to do this by hand calculations 100 years ago. And they were sitting for more than 4,500 hours computing the orbits here. If they were well trained, they could move the particle 3 steps per hour. So it was a lot of work to compute this kind of orbits of the particle in the magnetic field. So here is how computation has developed. From 1610 to 1900, the main tool for computation was the table of logarithms. That was really important. It was started with Kepler's work. Later, of course, you have these rulers to compute. Mechanical computers came in the end of the 19th century, but the main tool for much of computation between 1900 and 1950 was a room full of women sitting there computing things. Here is Margaret Hamilton. She was not really a computer in this sense. She was a programmer, but she was developing the software for the Apollo landing program and got the Presidential Medal of Freedom for this work. After the war, electronic computers started to appear. MANIAC, the mathematical analyzer, numerical integrator, and computer. And then the computer revolution took off. And it has been an exponential development since after the war in the speed of computers. So it's a Moore's law. Here's a diagram showing the speed of this is the world's fastest computer. The scale here is gigaflops. So one here is 1 billion computations per second. That's 1 gigaflop. This is the fastest computer in the world. This is the computer that is number 500 on the ranking of fast computers. And this is it is not exponential anymore. It's gradually flattening off, but it's still quite fast growing. It's exponential with a slightly lower rate now. But it's interesting to see that something like the iPhone, it is here. It's not a supercomputer in the modern terminology, but if you just go back, we see that already as short back as 2008, it would have ranked as the fastest among the fastest 500 computers in the world, the iPhone. And going back to 2003, it would have been the fastest computer in the world. So it's quite amazing about this development. Computational mathematics is the borderland between these 3 disciplines: pure mathematics, applied mathematics, and computer science. That's what I would say is the core issue of computational mathematics. Whereas computational science, I would replace the pure mathematics by applied applications, like physics, chemistry, and so on. My claim is that computational mathematics is playing a role in the bridging of the gap between pure mathematics and applied mathematics, because it can benefit from both perspectives, and it's providing new tools that is tying these things together. So let's look at the discussion we had so far. We have been talking about pure mathematics, where the goals is to classify general mathematical structures and relations between these by tools like global analysis, category theory, and so on. Abstract coordinate-free representations, category theory, homological algebra, and global analysis, differential geometry. Tools that languages, mathematical theories that are expressed independently of particular concrete representations, but in a general language that is taking into consideration the basic underlying structures of the mathematics. Applied mathematics traditionally has a very different goal. It studies concrete physical and mathematical problems. It is concerned with efficient computational algorithms, and the tools that has been necessarily so, at least in much of the 20th century, is concrete coordinate-based representations. We always use concrete representation of an object and compute on this concrete representation. It's important to find efficient ways of representing data and things like good basis for linear spaces. Computer science, the third of these three topics, has at least theoretical computer science has had is in some sense somewhat in between. The goals of theoretical computer science is to study the general structure of computational processes. It's interesting actually to say that to tell you that the basis of theoretical computer science was laid by Alan Turing before the war. And this was before the invention of computers. So the basic ideas of computability and efficiency of algorithms and so on was put down already by Turing before the existence of computers. But that's the computer science. Structured programming languages where you could formulate abstractions, efficient algorithms. The two in computer science, abstract languages, so languages where you can express abstractions. Category theory again comes in very naturally because you could consider certain computer programs as being a category. You have the arrows would be a program that do some transformation on the data. So the nodes in the diagrams could be the data, and the arrows could be the programs transforming the data. So category theory is coming up here also, tool from pure mathematics. Object-oriented programming languages, where you can combine abstract and concrete views of mathematical objects. That is really important and was a big inspiration for us when we started to look into this kind of ways to look at computational mathematics. So what is an object-oriented program? It's like C++ or similar or yeah, several of these languages. They have it's a central topic of programming. Modern programming is that when you have a computational problem, you should always ask what do you want to do and how do you want to do it. That's a basic division, and you should really be quite careful about separating these two. And then you build your computer software around classes. A class is then such a box where you have specifications of the operations you want to do, and there are algebraic relations between the operations. So it could be for a vector space, it could be that you want to have things like A plus B, you want to have A times B vector, you want to have basic operations like this. That's a specification that is guided by the underlying mathematical abstractions that you want to program. And then hidden in the class, the specifications up here is how this relates to other classes. If I have one class of vector spaces, it could relate to linear operators between vector spaces, and it could relate to other things. And then different classes communicate through this upper part, the public part of the class, and then there is a private part where things are hidden, and it's only visible to the class itself. That's how you represent the matrices. It is a sparse representation. It's dense representation, how the base so down here. It's a basic idea of object orientation, and this is something you learn when you study computer science, that you should try to organize computational processes around such an organization in classes. But in computer science, traditionally, they're not very interested in continuous mathematical structures. They don't learn it, and they don't know how to do it. And the problem is now, if you talk about things like differential equations and continuous mathematical computations, can this division between specification and implementation be taken seriously also in computational mathematics? This has been an ongoing theme for our research for several decades. So we started to discuss the concept of coordinate-free numerics. Can you do numerical computations without coordinates? Of course, you cannot do it, but because you always need coordinates in the end when you want to compute something. But you can still organize your software around this basic abstraction that you could think of things like differential manifolds, where you have the basic operations mappings between manifolds and so on, and you have the private things like we're really using that could be hidden within the class. And that turned out to be a very powerful way of organizing also numerical software. And we pursued this in the area of dynamical systems, differential equations evolving in time, where we took seriously the division between how and what, and we tried really to develop algorithms based on basic operations that made sense in mathematical setting. Abstract versus concrete again in computer science and computational mathematics. Modern programming languages allow for abstract formulations. It is possible to express abstractions in a modern programming languages. To find the correct abstractions, that's a difficult thing when you design software like this. And algorithms, can you devise algorithms that is relating to the underlying continuous mathematical structures? Yes, and in this task, the tools of pure mathematics, category theory, and global analysis are important tools for finding the right abstractions. A focus on fundamental structural properties of the problem helps the design of better algorithms and helps the design of better software. So I guess I have about 20 minutes left. That's according to my plan. Yes. So so a few examples where we can see what has been going on over the last 2 decades in this kind of abstraction, the use of abstractions in concrete computations. Yeah, one striking example is the work that has been done on the finite element method. So we saw the finite element method in this example. The finite element method is a way of computing partial differential equations by dividing the domain into triangles, and you build up a solution by building functions on each small triangle, and you glue them together and you find the optimal solution by calculus of variation. So that's the basic idea of a finite elements. These people, Doug Arnold, Rick Falk, and Rainer Winter, and others also, but these were instrumental, developed a theory of something called finite element exterior calculus, FEEC, where they looked into ideas of differential geometry, differential topology in the design of finite element basis, finite element discretizations of various types of systems, like elasticity problems, Yang-Mills equations, electromagnetic equations, and so on and so forth. So the finite element method, it's one of the most used methods in computational science. It's like this beer can here, or Coke bottle. If you want to compute the breaking of the bottle, and you divide it into small patches, and then compute by the finite element method. That's established, very well established technique in computational mathematics. What these people, Arnold, Falk, and Winter, did was to really look into what are the basic operations here in terms of so-called exterior calculus. So exterior calculus is a sequence of mappings where the composition of two mappings is always zero. So it's a way of organizing the principles of gradient, curl, and divergences, and many other examples. And what they did was to to look at the underlying continuous mathematics and discretizations of these, and try to find the correct geometric discretizations of the continuous complex. And out of this came naturally mixed finite element formulations, where, for instance, if you have the information on the nodes of this one and you compute the divergence, then you will get information on the edges. If you take the curl, then you will get information on the faces and so on. And if you go to divergence, you will get information on the nodes. And this way of viewing finite element methods has led to a revolution in the area of finite element methods, where they have invented new tools for understanding how to produce geometrically correct discretizations of various classes of differential equations. How they have organized the principle of many well-known but also new families of finite elements, and the tools they are using is provided by a continuous abstract mathematics, exterior calculus in differential geometry, the homological algebra, relating that's tools that are discussing this kind of it's similar to category theory. It's relating linear operators of such differential complexes, and this leads to new algorithms. It leads to new results on the stability of a finite element discretizations and so on and so forth. So it has really been a major conceptual change in the area of finite element calculus. I have been a lot interested in dynamical systems, mechanical systems, and other systems developing in time, ordinary differential equations evolving in time. I would say that before we started to look into this, so of course the task of computation of all these is you have the analytical solution here. That's, I write it like this, and you have numerical scheme where you step forward like Sturmer's problem. You stepped forward three steps per hour, and then you have numerically integrated. So before we started to look into this, we started in the mid 1990s. Then the most methods, essentially all the methods that were available in the books were based on the formulations of differential equations on vector spaces. And the basic operation when you advance the solution of the differential equation was to add to the solution like this. So you are in a point and you want to update the solution. You update by adding an update, and then you advance. So classical methods like Runge-Kutta methods, multi-step methods, they're all updating the solution by adding something. This is something you cannot do on differential manifolds. If you want to take seriously the idea that the good domain of a differential equation is not the vector space, but it is a manifold, then on a manifold you don't have this operation of adding things. You have points and you have tangents. Actually, in the classical definition of a differential manifold, you don't have a way of telling how do I move in a certain tangent direction. But you can, so that was necessary to introduce in this theory. We had to say something about how to move, and it was done by something called the group action. So we had a continuous group acting on the domain, and this group action was telling you how to move things. So and this led to a theory of so-called Lie group integrators, where you could use these abstractions that are defined independent of coordinate systems to define integrators for dynamical systems. At the same time, there was a lot of work going on in more general questions of structure preservation of differential equations. How can you discretize things so that you preserve certain important structural features? And there was a lot of work here. I don't think I have time to discuss it, but there were things like how to integrate dynamical systems like solar system or particles in an accelerator and so on. And many other questions where you try to find a numerical algorithm that in a certain sense is respecting the underlying abstract view of the problem. there were also established certain no-go theorems. So it turned out that not everything can be preserved exactly. You have to do some mistakes, but if you do your algorithms correctly, then you get a qualitatively much better result than if you are just thinking about errors as something independent of structure. So what we did in the area of Lie group integration was we started via an ordinary differential equation, and we thought of this as something living on a manifold, and we also always assumed that we had some group action that could be used as a building block to move the solution. And it turned out to be possible to make a very general theory of integration manifolds. So this was developed in a period over about 10 years, from 95 to 2005, and it has been going on later, but now it's more on the algebraic side of this. Here I'm coming back to the Northern Light again. This was the problem of Sturmer from 1907. Compute particles in the magnetic field. How do you do this with the Lie group integrator? You have to find a group action that you can compute, and that is somehow related to the original problem. This problem with the magnetic field of the Earth cannot be solved exactly. It is too complicated with the varying magnetic field of the Earth. But a problem that can be solved exactly is the motion of a particle in a constant magnetic field. If you have just constant line like this, then the particle would move in a helix like this. And this helical motion defines a Lie group action on the phase space, on the domain where the equations are developing. And then by this general theory of Lie group methods, you can combine this kind of motions to solve the more difficult problem of integrating things in a more advanced magnetic field. This is just one example. There are many other examples in optics and in mechanics and magnetization of hard disks. And there are really lots of problems where these kind of ideas have been used. So that was 3 examples: structure preservation, finite element exterior calculus, Lie group integration, and the 4th example, just briefly, is that we have done quite a lot of work on the applications of group theory, symmetry groups in computational harmonic analysis. And I don't have time to do it, but I would say that taking seriously into account the structure of symmetry groups, you can gain quite a lot of insight into problems of discrete Fourier analysis. How do you relate the discrete Fourier analysis that you can compute with the continuous Fourier transforms that you want to understand on continuous domains? This is all about relations between abelian groups. If you start to have other symmetries like reflection symmetries, then you have quite a lot of things to play with, like and this could lead to understanding of certain polynomials in approximation theory, which turn out to be hopefully important, and as they have not really been so successful as I hoped, but I still hope they will be. And also these kind of ideas can be used to exploit symmetries in computations of matrix computations. If you have a certain matrix that has certain symmetries, you can always use these symmetries to exploit the structure. And this is using something called the representation theory of groups. Medical registration problems, where you are taking pictures of a kidney and then things are moving, you can factor out the motions by considering groups. So that's also an important area of application where abstractions can help a lot. In pure mathematics, computations help pure mathematics? I would say yes, to a large extent. I think this is to me, this is the important developments that are taking place now. One is that computational mathematics is inspired by tools and language of pure mathematics, and the other one is that there are also inspiration going in the other is the area of mathematics called commutative algebra, where if you go three decades back, or 4 decades back, then the main books on abstract algebra, commutative algebra, was concerned with existence, uniqueness, classification of various structures, and not so much about how you could compute them. The invention of Grosvenor basis, which was a systematic way of treating polynomial systems, was revolutionizing this. Bergen developed this theory and devised computational algorithms for polynomial systems that were turning computers into a powerful tool for commutative algebra. Nowadays, in non-commutative algebra, they are getting inspiration from structures that arise in computation approaches on manifolds and so on. Differential geometry is enriched by computational questions. I think that once you start to ask about what you can compute, then the idea of differential manifold is a bit too weak. You need to say something more. You need to introduce things like group actions, and you need to say something about not just what is a tangent direction to the manifold, but also how can you move in certain tangent directions. And by exploiting this, it turns out that the new algebras appear that were not known in algebra before. Another example is the revolution that has taken place in the understanding of big data, and now computational topology is important in things like medical data acquisition and all sorts of big data. So what they do in topological data analysis is, for instance, if you have a point set like this, you want to make some geometric information about the point set. You start by drawing balls around the points, and then you compute something called the homology. That's really counting the holes of the domain. So in this first example, all the points are just separate. In the next one, the balls have grown to a point where they make a disk, a circle, torus, or a circle, and you start getting a hole. And then if you grow them more, you get a ball. So the idea of this was that you could grow the balls, and then you could look at the homology, counting holes, and then there's something called persistent homology, where you look at what sort of structures that live under many scales of this magnification process. These kind of ideas are now important. Algebraic geometry is coming into applications. SIAM has an interest group in algebraic geometry. The focus on computational issues, algorithms, and computation is unifying the mathematical sciences in the 21st century. That's my claim. I think that really now that the goal focus on computation is bringing mathematical sciences together again, because it is a unifying problem that is allowing computational mathematicians to discuss with pure mathematicians, and really there's a lot of benefit. We see that there's a lot of benefit from this interaction. It's not easy because we still have the cultural gap between the two communities, so it's not so that you can just sit down and immediately discuss with people from quite different culture, but both sides are now seeing that there's a lot to gain from such cooperation. I stop at this point. I think this is my optimistic view of the present century, the 21st century, that abstraction is bringing something new into computational processes. It is possible because of software developments. We see the benefit of it, and on the other side, computation is bringing something into pure mathematics. New mathematical structures are starting to become interesting because they appear in computational processes, and we really see that this cooperation between pure and computational mathematics should be bringing mathematical sciences together. So we see the need for developing these connections, and in a new effort now, we are creating a new research center between Tromsø in Norway and Bergen in Norway, which should be an international center where we bring together ideas from pure and computational mathematics. And we are now creating this center called Lee Sturber Center for Fundamental Structures in Computational and Pure Mathematics, where we bring together experts in various fields in a forum where we will have training of PhD students, organize workshops, conferences, and develop these connections between these two different areas of mathematics. So this is ongoing work. We are in the final round of something called the Centers of Excellence in Norway, and we already have some support, quite a lot of support for this. So we are really quite optimistic with the development of this center in the next decade. So that's what I'm doing now. I'm working on establishing this new research center. So Sophus Lee was the one doing symmetries of differential equations, and Carl Sturmer was the one doing the computation of the northern lights, and we think that they are representing the connection between pure and applied mathematics quite well. I stop at this point. Thank you.
Thank you, Hans.
Thank you for Professor MUNTHE-KAAS for the very enlightening presentation. And so we open the question answer session here. I have some of question in the chat. I think the first one is from Rizal Afghani. Rizal Afghani, can you will you ask directly to Professor MUNTHE-KAAS, or I can read your question? Yeah, Rizal? Oh, no. No response. So maybe I can.
Which question?
So
I see the chat here. So
yeah.
Yes.
So I can read the question from Rizal Afghani.
Yes.
His question is, what can we hope from homotopy type theory and proof assisted software in the future for mathematics? Yeah.
That's a very interesting question. I enjoy this. Well, I first of all, I should say that I'm not an expert in homotopy type theory. When we are creating this new center, we have explicitly said that we are not going in that direction. This is a new development in the foundation of mathematics and between mathematics and logic and type theory. But it's a very interesting development. So the question is really how to understand what is a mathematical proof, and people working in this area, they have developed certain programming languages like Coq, where they write a mathematical proof as a program. And by writing the proof as a program, it can be automatically verified by a computer. I think this is an important development in many ways. It was this Vobodsky who had his background from algebraic topology, who did build a theory around this Löf type theory, and it turned out that what he was introducing was the concept of homotopy on proof. So homotopy is continuous transformations, and they could introduce homotopy on proof, so that you could talk about two different proofs being essentially the same by you could transform one proof to another one, and you could talk about two proofs being essentially different by saying that they're not homotopic. And this is now considered to be a new foundation of mathematics. So you could build mathematics on set theory, you can build it upon type theory, and you can build it upon this homotopy type theory. The question is, can we hope for this? That automated proofs like this? I don't think that you will automate the discovery of the proof, but you can really automate and help the checking of the proofs. I don't think that all mathematics will be formulated this way. I think Vobodsky himself said that, yes, that's the only way we can do it. All proofs in mathematics must be formalized this way. That's what he died, unfortunately, a few years ago. But that was his view, that this is the future for mathematical proof. But I don't think that, but I think that it's important for certain areas, and I think that the ideas here are really important. So I think this is a very interesting and important area of research, but and I think it will definitely influence both the way we view the foundation of mathematics, what is a mathematical proof, and so on. But I think it will change a lot of things, but it will not be the. I don't believe it will be the only way we do mathematical proofs. It's a bit too complicated to me at the moment. In the New York Times obituary of Vygotsky, they said he was the man who explained equality, what it means for two things to be equal. So I stopped. It was a long answer. Sorry. I'm fascinated by this thing. I'm not doing it.
Okay.
Yes,
Thank you, Professor. And next question from Jeffrey Kusuma. About Jeffrey Kusuma, can you will you ask directly, or maybe I just read the question? His question is, what is the future of mathematics on quantum computer era?
Yes, what is the future of mathematics on quantum computer era? It's hard to say. Again, it's a topic I don't really work in myself, but I'm interested in following it. We are at a point where some people claim that we are achieving what is known as quantum supremacy, that there are certain problems that now can be solved more efficiently on a quantum computer than it could be on a classical von Neumann type computer. This is very much debated. There is a prominent mathematician who used to be a member of the Abel Prize Committee. It's Gil Kalai in Tel Aviv. He is writing a blog, Combinatorics and More, where you can read on these things. His view and claim, which is also controversial, is that quantum computing is impossible. That's what he says. Gil Kalai says quantum computing is impossible. It is a very delicate issue because now people claim that they are achieving quantum supremacies, and so now they are just at the point where quantum computers might be able to solve problems that you couldn't solve with traditional computers. But it's not clear, because when you look into the problems they've solved, people started to look into them and they found ways of doing it efficiently on the standard computers as well. So I'm not sure if there yet are any problems where you can establish that quantum computing could solve something that a classical computer could not solve. Of course, theoretically, there are all sorts of results, like you could factorize big numbers and so on and so forth. So there are a lot of results on the theoretical side, but the practical side is really what Gil Kalai is questioning. And this is when you have to have systems with many qubits, interacting particles and so on, that the problem is noise in the system. So you have to devise quantum correcting error codes to make quantum computing efficient and practical. And Gil claims that this is not possible for certain information theoretical reasons, but he cannot prove it mathematically, but he gives some evidence for this. So I think the next 10 years will be extremely exciting for quantum computing, to see if Gil Kalai is right or if he's wrong on his claim that quantum computing is not feasible.
Okay, thank you, Professor MUNTHE-KAAS. Sorry, we have to break first before we continue the question answer. So actually we should be in the break first. Professor Eddie?
Okay.
Yeah.
Okay, thanks, Bu Novriana. So we are going to present you some song, Professor.
Yes.
Okay, so this song is medley song, Indonesian folk songs, yeah, from various islands in Indonesia. So hopefully.
Okay. Yes.
Yeah.
Good.
Okay. Okay.
Professor Eddie, I think the sound is not
Really?
perfect. Yeah.
Uh-oh.
Should be in system. I think the
Uh-oh.
microphone should be in the same as system. You have to select a microphone.
Yeah.
The same as system.
Just sorry about that. So how to
In the Zoom platform?
the Zoom?
I think yeah.
The sound. Oh,
Zoom.
okay.
Yeah,
Okay.
the microphone should be in the same as a system.
Yeah.
The system.
Okay. Okay. Now we can do it now. Let's see. Just stop sharing. Okay. Small. Is it no? Okay. No?
Not yet.
Coba. Let me. No? Looking?
Yes.
Okay. Hopefully
Thank you.
you enjoy.
Brings back fond memories of my visit to Bandung in 2018.
Okay, good.
Thank you.
Thank you.
Yeah.
Thank you, Professor Eddie. Those are fabulous traditional songs from Indonesia, and they are in many languages that some of them are I don't know, because we have about 160 traditional languages.
Wow. But these people were from Sulawesi, was that so?
Yes, some of
them.
Sulawesi, Kalimantan, and then what else? West Java and others. Yeah.
Okay. Yes.
Okay. Let's continue the discussion. Yeah.
Okay. Let's continue and the question answer session here. There is a question from Arya Indrajaya. He asked about, will data science be the only math contribution to its financial industry, Professor? First, I will ask whether the data science including mathematics or not, or maybe what kind of data science that including in as mathematics.
So let's see. Now I lost my my chat. I don't see the chat. Oh yeah. So will data science be the only math contribution to financial industry, Professor? Yes. No, not at all. I think that the mathematical I think the mathematical contributions to financial industries are in many different areas, and data science is one of them. But another is a proper theory of stochastic differential equations. That's really stochastic analysis is the hard part of mathematics, and this is very important to financial industry. So in questions like how to price options and other questions of managing assets in financial industry, stochastic analysis is an important tool. So yes, data science is one, but not the only. I think that there's a lot of other contributions, and I think it's interesting that the financial industry seem, at least the advanced part of the financial industry, seem to benefit more from hiring mathematicians that they train in finance than doing the opposite, hiring financial analysts. It's not possible to train them in mathematics afterwards. So it's possible to train mathematicians to do financial things, but it's not easy to do the opposite. So I think as a foundation for doing financial mathematics, mathematics is financial questions is mathematics is important, very important. Yes.
Okay, thank you. So another question from Pak Yudi Suharyadi. I think you can ask directly to Professor MUNTHE-KAAS. Pak Yudi.
Yes, thank you.
Pak Yudi.
Yeah, I'm here.
Oh yeah, thank you.
Hello, Hans.
Yes.
This is Yudi.
Yes.
I chaired your
Hello.
plenary
Nice to see you
lecture
again. Yes.
a few years ago.
Yes.
Yes, I have a bit question, a little bit philosophical questions actually. So I see from your talk that the objective of the abstraction is compactifying mathematics, so that we have a smaller core, so it's more transferable for say next generation or so, right? But in the opposite way, we by doing more abstractions, we kind of alienate more people, so that just a few people, more elite people, can carry out the task.
Yes.
So it means less, say, more extreme survivability of mathematics. So how we balance those two seeming contradictory things?
I agree, and I think that I could have emphasized the negative sides of abstractions also, and I agree completely with your view. It is a big problem. I really don't know how to cope with it. It's a difficult thing. What should I say? I think that okay. Sometimes I think that abstraction could be can go too far. That it's not so that all results should be explained in the most abstract version. For students, I think most students like to really understand concrete examples before they appreciate abstractions. So that's important in the education, that you really pick good examples that illustrate the basic abstraction ideas. And but you cannot really push abstract mathematics on everybody. So I really don't know. It's a problem, and I agree with you completely, but I don't have a good answer. I think this is one of the major challenges for my own research in this Lie group integration techniques and so on, that we didn't really do enough effort to explain to engineers how to use our methods. They are applicable in many areas, but we haven't ever written things in a very transparent way, so that people in engineering can just pick up a book and say, here is how I can do it. And that's also an important thing to do. So I can just say, yes, I agree. I don't have a good answer, but it's an important thing, and it's balancing my optimistic view of this area, that abstraction is not always a good thing. It could also obscure things.
Yeah.
Yes, I agree completely.
Thank you.
Okay, thank you, Professor MUNTHE-KAAS. Another question is from Muhammad Ismail Yunus. Yeah, I read it for you. Greetings, Professor Hans. Is there a way we can use computational mathematics in developing bifurcation theory for more general parameter space, such as an n parameter space?
This I really don't know enough about this problem to be able to answer it. So that's my short answer. I really don't know it, so I don't know really. But when I was some years ago doing some work on exploitation of symmetries in computational mathematics and representation of symmetric groups in computational mathematics, I discovered that quite a lot of work in that direction was done by Algover and other people who were interested in bifurcation theory. So I would think that ideas from representation theory of symmetry groups could be applicable, but really I don't know enough about it to say anything certain about it. So I just have to answer, I don't know.
Okay, so I think, is there any question from audience? Then you can ask directly to Professor MUNTHE-KAAS. So how about I asked you about how about the data science? It is how can distinguish between the data science as just software development and data science as mathematics?
Yeah. Yeah, that's a very good question and difficult questions to me. Data science, it's of course a very important part of science now in our times, because there's so much big data. Data science is parts of it is new mathematics. There has been quite a lot of developments that are really mathematical in data science. Things like compressed sensing, where theory of sparsity in Fourier analysis and so on is important. So compressed sensing is an area where the mathematics is developed extensively in data science. Computational topological data analysis is coming in as a new tool that is developed a lot in data science. There are other techniques like machine learning. Machine learning seems to be extremely efficient, but according to what I understand, it's not really understood why it is working so well as it is. So that there's something lacking in the understanding of structural problems, structural properties of the problems that are used for machine learning. So I think that the mathematical foundation of machine learning is not well developed. It's not clear why these algorithms are working so well as they are. So. And I think that a lot of these problems here for the relation between data science and mathematics is that data science is a relatively new field, and that it needs to mature a bit to see what is important mathematical structures that can be used to explain things. I think it's very important. This thing is very important, and it's one of the most important things of mathematics in our century is the development of mathematics for data science. So that's yes, my answer.
Okay, thank you. I think time is up. Yeah, sorry. Do you okay that are you okay that is there any if there is one question more? Are you okay? Yeah.
Yes.
So it is from Muhammad Bakri. How to make the transition from concrete mathematics to abstract mathematics for undergraduate students? Should we introduce a transition course for first year math students, for example?
Yeah, it's difficult again. I think that an important thing is that there is a lack of communication between the two communities, and to communicate between areas of pure mathematics and the more traditional training in applied mathematics requires openness and new course, new ways of building up the courses. So I think that's what we will do now in the Research Center. We will make an environment where we'll have this kind of advanced or introductory courses where we bring together experts from the different areas and really let them sit together and work and develop common curriculums that are important for both the applied and the pure side. So it is an effort that is important and must be done properly. And we have which is traditional representation theory is something of pure mathematics, but we are making a new course now where the implication of representations in computation and in application is an important aspect. Of course, then you cannot go as far into the more finer details of the theory because you have to discard something. So we are trying to break the barrier between the two communities and create new courses that bind them together. It means that you have to take away something. You cannot go as deep in the pure mathematical side, but you can instead introduce more applications in the discussion. So it requires a bit of thinking about how to make good courses. And I'm not saying that everybody should learn abstract mathematics, but I think there is a room for some students to work in this borderland, and they should be offered courses where they can interact. And the important thing is to be open in a discussion between different experts. You cannot expect that people understand each other when they sit together, and you have to allow for enough discussion and time to interact properly.
Okay, thank you, Professor MUNTHE-KAAS, for the excellent session there. So I will give it back to Professor Edi Tribaskoro. Thank you.
I'll just say that I really enjoyed this session. I think it was lots of very interesting questions coming up here, and I'm quite impressed. So I think that was very interesting. Thanks a lot to everybody for participation. Edi.
Okay. So thanks again to Professor Hans MUNTHE-KAAS for wonderful and inspiring lectures today. So for our appreciation, we would like to present you a certificate of this signed by our dean, and then
okay, very nice.
I'll give you present you a sketch of your photo. So okay, let me show you now. Okay. Yeah. Okay, so this is the certificate.
Nice.
This appreciation. So thanks, Professor Hans, and also just a moment.
Nice to have in the office.
And this is your photo.
Yes. Thank you.
Okay, so I will send.
Very nice.
I will send these two documents to you. And
thank you.
Okay, so again, thank you so much.
So we should organize a possibility of visiting sometimes. I'm a bit tired of just sitting here in Norway now. I hope we can meet.
And also congratulations to your center. So to your new center, yeah. So
it's something that we are just starting. I'm not sure how official things are, but we are getting enough support to know that this will be something. But we are in the competition of this Center of Excellence in Norway, and it will take another year to decide. So it's really quite exciting to see the next year if they are really going to give us lots of support for this, or if you have to how we have to do things.
Okay,
it will mean in practice that I will have a divided position between Bergen and Tromsø. So I will divide my position in two.
Yes, excellent. So okay, so now we end to this program. So thanks to everybody for being with us today. Hopefully you get some benefits from this program, and see you again on next month, sorry, not next week. So we will have the last one, which is Mathematics Distinguished Lecture Series given by Professor Richard Boardi from USA.
Yes.
So see you all next month. Okay, thanks, Hans.
Thank you. Bye-bye.
Thank you, Professor Hans.
Thank you.
Ya, Pak Yuli, terima kasih banyak.
Sama-sama, Pak Edi.
Ya. Terima kasih supportnya, Pak Yuli.
Pamit, Pak Edi.
Oke. Ya, terima kasih banyak. Terima kasih banyak. Oke, Pak Yudi. Terima kasih Bu Novriana. Thanks. ya semua
Sama-sama,
komite
Pak.
ya. Oke, Bu.